everyone. Today we are going to discuss the dynamic building design for a boutique hotel in Sydney, Australia.
A dynamic building facade is an exterior surface of a building that can change its physical properties or configuration in response to environmental conditions. It enhances the building's energy efficiency and thermal comfort, reduces reliance on artificial climate control systems, adapts to changing light, temperature, and air conditions.
The concept of dynamic building facade is vital as it brings energy efficiency, climate adaptation, user comfort and well-being, and architectural innovation. They represent crucial advancement towards sustainable, adaptive, and human-centric approach to architecture, addressing both environmental and social needs to the modern world.
Exploring key components of a sustainable hotel design with a focus on a kinetic facade as a central feature. By focusing on the climatic data, site-specific analysis to guide design, by making material choices which are eco-friendly and responsible selections, energy efficiency, integration of advanced sustainable technologies, and adaptive design elements that respond to environmental changes, enhancing energy efficiency and comfort.
For our case study, we chose Al Bahar Towers. It's a Mashrabiya-inspired kinetic shading system, parametric geometry simulation, adjust panels to the sun movements, reducing solar gain and glare. A screen opens and closes dynamically, tracking the sun's path. At night, panels fold, revealing more of the building's facade.
Our second case study is the single-skin kinetic facade, which is Kaifer Technic Showroom in Australia. The facade consists of moving aluminium panels integrated into a single-skin facade. The panels adjust dynamically to control sunlight and ventilation. It provides shading without a separate secondary skin, enhances visual interest with dynamic movement, reduces glare, and improves occupant comfort.
The aim of the project is to study a building located in a temperate climate with specific site constraints and orientation. It explores innovative solutions to optimize the indoor environment and reduce energy consumption.
Our location is Sydney, Australia, which is accessible to Military Road that connects to Bondi Beach and surrounding suburbs. Camp Pilparad that connects the beachfront to Military Road, providing scenic access to pedestrians and cyclists from Bondi Beach. Huge Bamford Rivers includes grassy park areas, sports field, and picnic spots. It also offers recreation opportunities with stunning natural views. The site is enriched by diverse outdoor activities, making it attractive to both locals and visitors seeking leisure and natural beauty. These graphs illustrate that summers have long daylight hours and high solar radiation exceeding 1000 watt-hour per meter square per hour. Temperatures often exceed 35 degrees Celsius, surpassing the comfort zone. In winters, short daylight hours with solar radiation dropping below 600 watt-hour per meter square per hour. Average temperatures fall below the comfort zone, indicating a need for heating. In spring and autumn, transitional seasons where mean temperatures are closer to the comfort zone.
To achieve indoor climate control, various strategies could be employed as highlighted by the below diagram. Sun shading of windows 11.4% to reduce heat gain. High thermal mass 5.4% and 4.4% to moderate indoor temperature by absorbing heat during the day and releasing it at night. Evaporative cooling 6.4% to effectively lower temperatures in hot dry climate. Natural ventilation 9.5% to promote cooling by harnessing outdoor airflows. Heating and humidification 16% to ensure comfort in cool, dry conditions.
Talking about the sun direction, the sun rises in the east and sets in the west, but due to Australia's southern hemisphere location, its midday path is tilted northward. At noon, the sun is positioned higher in the sky compared to the locations in the northern hemisphere, leading to a more direct solar angle, particularly during the summer months.
Now discuss the base case of our building design. Goal of efficiency and optimized case is to increase energy efficiency and reduce carbon production. The kinetic facade will contribute to the hotel's sustainability goals by minimizing reliance on mechanical heating and cooling system. It will further optimize natural ventilation and light. The tensile fabric will help create structure that is both energy efficient and visually compelling.
Designing a boutique hotel along the coast of North Bondi presents an exciting opportunity to blend luxury, sustainability, and innovative design. The hotel features three floors, each spanning 500 square meters. The ground floor comprises a restaurant, lounge, and reception area, creating an inviting space for guests and locals alike. The first floor includes well-appointed bedrooms that offer comfort and style, while the top floor is dedicated to presidential and standard suites for VIP guests, each with stunning sea views. The layout maximizes the hotel's connection to its coastal environment, ensuring that every guest can enjoy the beauty of the ocean.
These are the rendered images of the hotel.
Overhangs were used as part of a dynamic facade system as we had a small building which had three floors and it was up to 10 meters in height. Overhangs block direct sunlight during peak hours, especially in summer, reducing solar heat gain. Properly designed overhang allow winter sun to penetrate and provide natural heating while shading in summer. Reduces reliance on HVAC system by maintaining indoor temperatures. Overhangs were used as part of a dynamic facade system as we had a small building which had three floors and it was up to 10 meters in height. Overhangs block direct sunlight during peak hours, especially in summer, reducing solar heat gain. Properly designed overhang allow winter sun to penetrate and provide natural heating while shading in summer. Reduces reliance on HVAC system by maintaining indoor temperatures.
Use of tensile fabric panels can harness wind energy for natural ventilation, while limiting excessive wind speeds in critical air zones, enhancing comfort and energy efficiency. The design process included the zoning of the ground floor, first floor, and the second floor. In order to create a sustainable design, the zonings were recreated in Design Builder.
In this slide, the sun paths are showcased following the daylight across three different seasons, same date and time.
The CFD simulation shows air pressure throughout, around and over the building. The greatest pressure is felt across the eastern wall due to the Pacific winds. CFD simulation shows the wind accelerating as it goes over the building.
The base case was built keeping in consideration the Australian building codes.
Chart shows the layers of the flooring as per the Australian building code. Minimum standard of the Australian Building Code. The Green Star credit IEQ status was fail as we just met the 5.4% of the meeting requirement.
Green Star rating system in Australia. Green Star is widely used in Sydney and across Australia, encouraging the construction of environmentally friendly and sustainable buildings.
Strategies used, we met 46% of the requirement area, which gave us 1 point for the Green Star credit.
Use of tensile fabric on kinetic facade as a shading device. The fabric can act as an adjustable shading element, allowing the control the amount of sunlight entering in the building. Its flexibility and light diffusing properties can block direct sunlight while still permitting natural light, thus reducing cooling loads and enhancing energy efficiency.
As discussed previously, changing the hue value by changing the material has led to varying results. We managed to decrease the carbon dioxide production by decreasing the reliability on cooling for electricity.
In material selection, the facade will utilize high-performance tensile fabrics known for their lightweight, flexible properties. These fabrics are often made of durable materials like PTFE or PVC, which are resistant to weathering and UV degradation. To enhance its adaptability, the facade may incorporate sensors that monitor environmental factors like sunlight, wind speed, and temperature. These sensors can trigger the mechanism system to adjust the facade configuration accordingly, optimizing natural light and ventilation.
Wind interacting from variable directions with dominant winds from the southern end and secondary Pacific winds from eastern end. The wind rose diagram suggests no calm period with 2% inland winds from the west side. The below data is calculated with at 10 meter from the ground. Velocity of 6 meter per second in the area ranges between 4 to 8 meter per second. Considering the wind velocity and the varying wind direction, small scale wind turbines are employed as a renewable source of energy. Varying wind patterns, Saviour's turbine is used, the coefficient of which varies between 0.15 to 0.3530. These figures are taken from Urban Green Energy and Windspire, the top manufacturer of vertical wind axis turbines. The calculation for the wind turbines considering the average wind speed 6 meter per second. Assuming the operating capacity is 40% of the year, 654 kilowatts per hour per year can be generated from one turbine. We will be using 4, so that would be 2616. By incorporating dynamic facade that follows the sun path and redirects the wind towards the wind turbines, we managed to cover 100% of the area, meeting the requirements of the Green Star, and acquired 3 points.
Incorporating a kinetic facade made of tensile fabric into the boutique hotel design enhances aesthetic and sustainability. This innovative approach improves energy efficiency and aligns with the goal of reducing carbon footprint, showcasing how architecture can adapt to its environment while creating functional and beautiful space.